We need to talk about sorting, right? I mean, it's about time. Sorting is kind of a big deal, and yet we usually take it for granted. If you think all the way back to lecture 1, I just wrote sort A in some pseudocode, and I argued that, yeah, we all know sorting is possible, no big deal. And then in lecture 2, I claimed, pretty much out of nowhere, that it's possible to sort a sequence of n items in n log n time. Well, I guess I have to justify that, so it's about time we talked about sorting. Now, I can sort arrays and I can sort linked lists, and we're just going to spend the next couple of lectures talking about different ways of sorting stuff. One of the things we're going to discover is it turns out it doesn't make much of a difference whether I'm sorting an array or a linked list as far as asymptotic complexity is concerned, at least for the algorithms that we are going to talk about. It's true that for some algorithms, if I choose to implement them using a linked list, maybe there are some parts of the algorithm that are much more elegant or easier to write or more convenient or even faster. But for one reason or other, it turns out the asymptotic running time of the entire algorithm always ends up being pretty much the same, array or list. Some part might be easier, but some other part might be just as difficult if I change data structures. So it's true that we do take sorting for granted. We take it for granted as algorithms people a lot of the time, as I have done. So I mean, I'm guilty of this as well. But we take it for granted as programmers as well. So if we're programming in one of our favorite languages, so if I want to program in C++, or if I want to program in Java, or if I want to program in Python, and I decide that I want to sort something, it doesn't even matter what I'm sorting. If I want to sort an array of pretty much anything, I just go and call a standard library function, and it's pretty much dead easy. I might have to provide some basic information about what sorting means, and that is something we do need to think about. But once I do that, I just call a library function, and my sequence comes back sorted. And that's one of the reasons why having a programming language with a standard library is so nice. Now, I mean, C people are hearing this and sobbing quietly to themselves because although C does actually have a standard library that provides sorting functionality, it's not everybody's cup of tea. So sorry about that, C people, but you're probably used to it by now. I love C. C's great. But yeah, C isn't so great for that sort of thing. So what I want to talk about today is what is called comparison sorting. I want to talk about the kind of sorting that would be done by the standard library function that takes care of sorting in your favorite language. And if you think about it, if you've ever used those standard library functions, you realize they can sort just about anything you give them. You have to provide them very little information about your data for them to be able to sort it. And that's a good model to use for our exploration of sorting. Although I will also talk about the alternative. So today we're going to talk about comparison sorting algorithms. And I want to talk in the next lecture a bit about the alternative, non-comparison sorting, although I can only really touch on that subject because that is the kind of thing, if I am allowed to take into account lots of properties of my data, there are all sorts of directions I could go with that. So the next lecture will mostly just be a taste of what I might be able to do if I am allowed to read into the structure of my data further. So the idea behind comparison sorting, in the meantime, we'll just spend this lecture talking about comparison sorting. The idea behind comparison sorting is that an algorithm that performs comparison sorting doesn't need to know very much about the data that it's sorting. It just needs to understand that the data can be compared with other elements in the same sequence in some logical way. In other words, if I give you some array, let's just call the elements of the array, we'll do A1, A2, A3, and so on. If I give you some array and I tell you, it's none of your business what type these elements are. However, if you want, you are allowed to compare two of them together. So I'm going to give you a less than operator or a less than or equal to operator. Or of course, I could just give you a function that returns true or false. If A is less than B, it returns true, otherwise it returns false. I give you some way of comparing two elements in the sequence, and that is all you are allowed to use to understand the ordering of things in the sequence. And that's the model of comparison sorting. So you know nothing about the type of your data except what is exposed by this operation that you were also provided from outside. So if you're the sorting algorithm, it's none of your business exactly how this operation works, but it is reasonable to assume that this operation works like any other less than or equal to symbol. In other words, suppose that you discover that some element A is less than some element B, and you discover that some element B is less than some element C. For this comparison sorting framework to work, reasonably you should be able to assume that that implies that A is less than C. That is the property of transitivity. So you can assume that this less than operation that you've been given works properly, but it's really none of your business exactly how it comes up with its answer, only that it gives you a well-defined true or false answer in each case. As a result, it's sort of useful when we talk about comparison sorting to think about it in terms of sorting a set of, I don't know, abstract, inscrutable things where somebody outside has defined some ordering over the elements. So in other words, suppose that the set of things I'm sorting is drawn from this collection of 5 symbols. And somebody, somewhere, has decided that clover comes before star in the finished ordering. So if you get an array full of these symbols, they provide you some way of deciding, if you give it, let's say, clover and star, some operation that tells you, yes, clover comes first. And the way we want to think about this is that that order is completely arbitrary. So the elements make no sense to me, like I have no idea what they really mean, and the ordering also doesn't really make much of a difference. It's just a well-defined ordering somebody else came up with. And they could come back tomorrow and they could decide that actually they want the opposite ordering. Or they could decide they want some strange variation on this ordering, and that's fine. As long as they can define a comparison operation that works out that way, that's fine. And the comparison operation just takes any 2 elements and returns true or false if the first one is less than the second one. And so the idea there is that way, if I constrain myself to that model and implement an algorithm for sorting based only on that less than or equal to operation, then I should be able to sort just about anything where that operation can be defined. It's also worth noting that really it makes sense that anything that can be sorted should have some less than operation you can define, right? Because if there is a sorted order, there must be some way of comparing elements. There must be something that can induce that order. And so the idea there is that way, if you write the algorithm today and it uses this general comparison sorting framework, then a data type that isn't invented yet or hasn't even been imagined yet could still be sorted by your algorithm later, because as long as we can define the less than operation, we can use the comparison sorting algorithm. Now, I guess the next question is, okay, so we have a less than sign. What does sorted mean? And this is a bit of a formality, but you know how I am about formalities. We sort of need it in a course like this. There's a few ways of defining this. I'm going to use array-like notation. So as I said at the beginning, it doesn't make much of a difference for our algorithms, whether we're sorting an array or a linked list. But for the sake of visualization, it's generally just easier for me to use arrays. So I'm going to do that for most of this lecture. I will point out a few cases where a linked list might make things easier, but it turns out it still doesn't make things asymptotically any faster. And so I'll define a sorted ordering as follows. I take this array, so here's your input array, and I define some ordering. I give you a function that evaluates, it takes 2 elements and tells you which one comes first. And then this apparently is the sorted result. And I think if you look at it, it does look as if it complies with the order on the top. The question is, how can I state that formally? Okay, I'll do it like this. Pick any 2 indices I and j where I is less than j. So we'll do maybe these 2 here. And it must be the case, no matter which 2 I picked, as long as I is less than j, that a at that index, a sub I, is less than or equal to a sub j. And if that criteria holds for every pair of indices I and j, where I is less than j, then we'll define the resulting sequence is sorted. Now, this is actually a bit more general of a condition than I really need. It actually would be sufficient to define something like to say that for all indices I, a of I is less than or equal to a of I plus 1. And you realize that because of that assumption of transitivity, that is, because if we assume that clover is less than star and star is less than pot of gold, then that should mean clover is in turn less than pot of gold. Then it actually turns out that this is equivalent to this. But for the sake of stating something very general that's very easy to justify, this is my condition. And I did use array indices there, but frankly, we could always use indices on a linked list if we want to state a definition, although evaluating the operation of finding an index of a linked list might be a bit tedious, might be a bit difficult. And so keep that in mind, that this condition applies just as well to linked lists, but the notation is a little bit more unpleasant. It's not as easy, it's not as intuitive, I guess, to write it out that way. Okay, so that said, so I think it's good when we think about comparison sorting to think about the things we are sorting as being some strange abstract object where we have no idea what it really means, and we also have no idea what it means for one to be less than another, just that somebody else is taking care of that problem for us. Okay, fair enough. However, it's also true that when we're teaching sorting algorithms, when we're trying to learn new things, it is useful to employ our brains, which are pattern recognition machines, to develop intuition about stuff. And so let's write out an array of numbers here for the sake of demonstrating the point I'm trying to make. Here's an array of numbers. and we'll see a few of them because of the excuse I'm about to make. Basically, my argument here is that, yeah, if you assume all of your arrays are always numbers when you're sorting things, you might jump to conclusions that we shouldn't draw. That is, there are certain things that we know about integers that don't apply to arbitrary collections of objects. Because, for example, I could look at this and say, you know, I'm pretty sure all of the one-digit numbers are going to come before any of the two-digit numbers, which are going to come before any of the three-digit numbers. Yeah, that's probably true, and save that thought for the next lecture. That is actually something we can observe about integers, but it doesn't really map on to arbitrary symbols. I mean, we could always pretend the arbitrary symbols were integers, but then the matter of what it means to be 2 digits versus 1 digit doesn't map on easily to that abstraction. So if we use only arrays of integers to study sorting, we might get bound up in some assumptions we're not really supposed to make. Okay, great. That was a great argument to use the symbols, but then I'm going to spend the rest of this lecture just talking about arrays of integers, and here's why. Because intuitively, if I look at an array of integers, we know enough about numbers, we've worked with numbers our whole lives. For example, you can glance at this and you can probably already tell that -5 is the minimum element. You could look at this and find the minimum element too, but it would require more thinking, more cognitive load. And that makes it very hard to develop intuitions. So because we know about numbers, yes, we are going to use numbers. Just be careful. We don't want to make any assumptions about integers that don't apply to general abstract symbols in our sorting algorithms. All right, so here is our cast of characters. This can be our character select screen for our coverage of sorting. Now, there are tons of sorting algorithms out there, tons of them. And I think like the best, resource for finding information about all the different sorting algorithms around that I've ever seen is the Wikipedia article called Sorting Algorithm. So just look that up and you'll see, I think they have a table sort of like this that just lists a whole ton of algorithms, groups them into categories, talks about their running time, talks about, in some cases, whether one algorithm is a variant of another. It's fantastic. There are tons of sorting algorithms out there. Many of them are variants of some other algorithm. I don't claim that these are the original variants of their type, although I think some of them actually are. The reason I've chosen to cover these ones is I think that they cover all the bases as far as showing off the different approaches to sorting. I also think that they cover all of the important algorithms that every algorithms person ought to know about. So for example, every algorithms person pretty much ought to know about merge sort, they ought to know about quicksort, and they ought to know about all three of these things. There are tons of other algorithms though. Many of them are really interesting, some of them are really weird, and it can be useful to take a look at them just to get some perspective and maybe decide whether you agree with my selection. Now, as far as today's lecture goes, we're not going to talk about this. Frankly, when I see a table like this one, my eye goes immediately to this row because it's the most exotic looking algorithm in the table. However, not today. We'll talk about that in the next lecture. That's a non-comparison based sorting algorithm. We are also not going to talk about heap sort for the very practical reason that we don't know what a heap is, and that when the time comes to learn about heaps, I think right now the heap lecture is about, 160 slides and counting, so I don't think we have time today to cover heaps. So we'll leave that off. By the time we get to heap sort, once we learn about heaps, it turns out that employing heaps to perform sorting is pretty easy, so it'll be a bit of a footnote when the time comes. So I want to spend today talking about these 4 algorithms. And I want to talk about all of them in the same lecture because I think that there are some startling similarities that each pair has with its complement. That is, I think that insertion sort and selection sort are sort of duals to each other. They're sort of two sides of the same coin. I also think that merge sort and quicksort are sort of twins. They're sort of duals in the sense that they both perform a very similar operation. They just, where they perform the work is transposed between the two algorithms. And so the case I'm going to be making over the next, over this lecture is that we've got these selection-based algorithms like insertion sort and selection sort, and even though they have very clear differences, so if you look at each line of the table, for example, the best case running time is significantly different, I believe that they are actually siblings. They are actually dual to each other. And same thing with merge sort and quicksort. It's clear there are differences between merge sort and quicksort, but I think that actually fundamentally they are exploiting the same basic technique just in two opposite ways. Okay, so there's our character select screen. Which character are we going to select first? Selection sort. Excellent choice. So let's take a look at this array here, and the task is quite simple. Design an algorithm to sort this sequence of integers. And so let's use our intuition. We know that it's not currently in sorted order. Okay, why do we know that? Well, my eye goes immediately to this thing. So 187 clearly does not go at the beginning if this is a sorted array. Why do I say that? Well, because if I skim over the elements of the array, this is the minimum element, -5. And one thing I know about sorted sequences, no matter how generally you define them, so comparison-based or otherwise, is that in a sorted sequence, you should expect to see the minimum element first. So I think, if I want to make this array a little bit more sorted, then I want -5 to be here. But the problem is, pretty obviously, there's already something there. So 187 is occupying index 0. Okay, how about this? I'm going to put -5 there. And we'll just put 187 here for safekeeping. I can't delete it, obviously. I have to keep it around, so we'll just swap the two of them. Great. And once I've done that, my array is now a little bit more sorted. I now have an array that is sorted up to the end of, index 0. So one element of my array is in its final sorted position. That's interesting to note. It's not only do I have a one element sorted array at the beginning of my sequence, but -5 will never move. That is where it's going to be in my final sorted order. Okay, so I stare at what's left over, and I want to ask the question, can I make any further progress? Okay, well, -5 is done. I don't have to worry about it ever again. So I can sort of pretend as if the array is just these 6 elements. And I think, yeah, the same observation sort of applies. This is clearly not sorted, because in the sorted ordering, -1 should be at the beginning. All right? And then I think, I could try the same trick again. I could just put -1 here and move 10 over just for safekeeping, put it in index 6. Okay, so I perform that swap. And I realize that when I'm done, I now have, at the beginning of my sequence, 2 elements in their final sorted position. And hopefully it's clear now what I intend to do. I'm just going to repeat that logic over and over, and at each step, the size of my sorted portion is going to increase. There we go. And now I have a sorted portion of size 3, size 4, size 5, size 6. And actually, I can stop here. Even though technically this is still the unsorted portion of the array, this sequence has size 1. And a good observation to put aside for later is that any array of size 1 is automatically in sorted order. You can't be out of order unless there's at least 2 things to be in the wrong order. So I get this one for free. If I can sort the first n-1 values of my sequence, the last value, whatever's left over, is automatically the largest value and therefore belongs in the last index. All right, and I call this selection sort because at each step, what I did was I walked through the elements I had left over, the remaining unsorted elements, and I selected the minimum element and moved it into the first position. And at each step, my sorted sequence got 1 position larger, and my unsorted sequence got 1 position smaller. Here is some pseudocode for an array-based selection sort. As I said earlier, I'm focusing on arrays for the sake of the lecture because showing the pseudocode for both linked lists and arrays doesn't seem to help that much. It just clutters things up. And because if we talk about linked list pseudocode, we have to spend a lot more time negotiating details of how the linked list works internally. Is it a doubly linked list? How do the pointers look in the pseudocode? None of which we really care about for sorting. What I will observe for this array-based pseudocode is obviously when we go and find the minimum element, we use array indexing to find it. But this operation here could be done on a linked list as well, and it would take just as long. I just walk through my linked list and find the minimum element. Here, I'm swapping elements. Now, with a linked list, I don't need to swap elements, although I can do that. If I have 2 nodes, I can move things between them. So, if I have a linked list that looks like this, and I have, let's try the 187 and -5 example again. If I do actually have 2 nodes that have values that I want to transpose, obviously I could swap. I could also actually structurally modify the list. I could take the -5 out here and reinsert it at the beginning, and that would be constant time, whatever. I can do these things with a linked list. So hopefully you can convince yourself that none of what I've written here as pseudocode for selection sort or any of the other algorithms really changes that much if I do stuff with linked lists, besides the obvious changes to mechanics of how the list works. There's nothing that gets any faster. Okay, so then the question is, how fast is this algorithm? So to clarify, what I'm doing is I'm walking through all indices of A, so I is 0, 1, up to n-2, because I can skip the last index. And the goal of the outer loop is at the end of each iteration, position I will now contain its final sorted value. So at the end of iteration 0, as we saw, the element in index 0 will be the -5, will be the minimum element of my array. Okay, so to do that, I have to go find the index of the minimum element. So I start at index I look at all future indices of the array, and I just choose the minimum index, so we know how to do that. And then at the end, this if statement, I actually don't need an if statement here. I could do the swap either way if I wanted to. But at the end, if the thing I find, the minimum element, is in the wrong place, do a swap to put it in the right place. So my analysis, we can skim over this because the analysis, this is a pretty basic algorithm as far as we are concerned. It's just for loops and constant stuff. So we don't have to do a very detailed analysis to conclude that it turns out the running time is actually n squared. Now it says exercise, but I'm actually going to sketch out how I get there. So this loop here is clearly big theta of n. I mean, it has n minus 1 iterations, but that's big theta of n. However, we've got the situation with this nested loop where it's not clear exactly what it is, or I mean, we probably can guess, but the running time isn't something that jumps out at us. Like it's clear that the number of iterations depends on I, so we could draw the usual table of values of I and the number of iterations of the inner loop. So, okay, we'll just draw that out. All right, so when I is equal to 0, j starts at 1 and goes up to n minus 1. So there are n minus 1 iterations. When I is 1, there are n minus 2 iterations. Now you see where I'm going with this? When I is equal to 2, there are n minus 3 iterations. And then I get down and I think, okay, so when I is equal to n minus 2, there'll only be, let's see, so when I is equal to n minus 2, well, I start j at n minus 1, and I go to n minus 1, so there's only one iteration. And I think, yeah, this reminds me of something that just keeps coming back up in this course. So you recall back in lecture 2, I brought up how important this identity was, and I hope by now you understand that I really wasn't kidding about that. So what I'm doing here, if I add up the total number of iterations of the inner loop over all iterations of the outer loop, I find myself basically back in lecture 2 analyzing that contains duplicates algorithm. And I'm just adding up all the numbers from 1 to n minus 1. So I'm doing this sum here. I guess I'm not going to use I in my sketch because I is in the algorithm. So I'm just adding up the values k is equal to 1 up to n minus 1. And we know already, because we've just seen this over and over again, that turns out to be this number. And n times n minus 1 over 2 is big theta of n squared. And that is why I can conclude, I've just basically done the whole exercise here, that is why I can conclude that selection sort is n squared in the worst case. One interesting observation, though, while we're thinking about this, is that if we characterize, I mean, it's true, it is n squared in the worst case, yes, but what's the best case? And actually, it's the same. If you notice, the number of iterations of the loops are not determined by anything to do with the contents of A. It's certainly determined by the length of A, but not the contents. Some of the work in the algorithm certainly depends on the values in A, obviously. Like that is, whether I get inside this if statement at a particular point does depend on the values of A. This is all constant time stuff. I guess I assumed that in my previous analysis, but hopefully it's clear by now that these if statements are all constant time. And so, strangely, the algorithm is actually going to be n squared in every case. So, best case, expected case, worst case, any array you give me, it's going to be n squared. It might be a little bit better of an n squared in certain cases. That is, if I get into this if statement a bit less often, then yes, it might take fewer operations, but only a constant number fewer. And so selection sort is n squared in all cases. And I suppose that's why it's nice that we started with it, because it's not going to look too good after we've seen faster algorithms. But I do want to take a moment to appreciate it, because selection sort actually does have its value. It's easy to say, oh, well, we could use merge sort, which we'll learn later is faster. Yes, but merge sort is a bit of a pain to write, and it requires more work, and it takes longer to test. Whereas selection sort is the kind of thing where once you know how it works, you can write it from memory if you need to. And if you find yourself working in an environment with restrictions, so suppose one day you have to write a sorting algorithm you have to write it in assembly language and run it on an embedded system. Well, hey, selection sort's great because you know in advance that it's only going to need iterative these basic for loops that iterate over indices, 2 of them, and typically those are simpler to write than a lot of other conditional things or recursion or whatever if you're writing assembly language by hand. And the logic is relatively simple. So there are cases where, for lack of any better idea, selection sort is a great way of bootstrapping your way into having a sorting algorithm. Because it's true that, yes, at the end of the day, when we are programming out there in the world in our favorite high-level language like Java or Python, we probably don't need to write sorting algorithms from scratch, but having the ability to do so is useful because strange cases come up where you need to do it. There are other weird benefits of selection sort that have to do with the fact that that the branching structure doesn't really vary that much for different arrays because every case has the same running time. There are reasons why this can be quite helpful. They're very esoteric, though, from our point of view. So one of the reasons reasons is that suppose you're programming in an environment where you only are sorting small arrays, like all of the arrays you sort have size 20 or something. Now, selection sort may still not be the best choice for that in general because it does do more work than it needs to. However, because selection sort takes pretty much the same amount of time on every array, if you're working in a context where you need to guarantee an absolute number of instructions at maximum for sorting, selection sort does give you an easy way of making that assumption because it's very easy to predict exactly how long it will take. So I like selection sort. It's the algorithm that I write when I need a quick sorting algorithm, and I don't have recourse to the standard library in my favorite language. But it's true, unfortunately, that selection sort is much slower than all the other algorithms we're going to see today. Speaking of which, we find ourselves back at our character select screen. Well, which one's going to come next? Okay, insertion sort. I think that's a good complement to selection sort. I didn't mention this earlier, but of course, I won't talk about, I'll expand on what I mean by these two columns later on and in the next lecture. So it's not, I'm aware I haven't yet defined what these two terms mean. All right, so task. Here's the same array as before. Design a different algorithm to sort that sequence of integers into ascending order. Okay, I'm going to demonstrate insertion sort twice. I'm going to do it the first time using a second array because I want to make it really clear what I'm doing at each step. And then the second time I demonstrate it, we'll just do it all in the original array, as we did with selection sort. So one thing I didn't make a big deal about with selection sort, but that should be evident, is that it's able to do all of its scratch work inside of the array. It needs a couple of local variables, but it doesn't need to allocate a new array. The version of insertion sort I'm going to talk about first does that, though. So I'm going to make a new empty array called B. And the goal is, as I go through A, I'm going to build up B to be a sorted sequence. And we can regard B being sorted as an invariant. So at every step of insertion sort, the elements currently in B, so if I ignore all the empty space, the elements in B will always be in sorted order. I might rearrange them every now and then, but they'll always be in sorted order. And so the goal of insertion sort is, I grab an element from A at each step. I'm just going to go left to right through A. I grab one element at each step, and at each step I put that element into B, maintaining the sorted ordering of B. Now, for the first element, that's going to be very easy. I just drop it right in. For the second element, so here I have 10, I obviously have to make sure, as I said, that B is in sorted order when I'm done. So I think to myself, okay, well, the B is going to have size 2 when I'm done. Can I put 10 here? Obviously not. Well, wait, why not? Well, because 10 is, okay, wait a minute. I had it the right way. Okay, I'm thinking the wrong way around. 10 is less than 187. 187 is greater than 10. And so I can't put 10 in position 1. So what do I do? Well, the way I think about this, and it's mostly a preference because you could start at the beginning and work forwards. The way I think about this is start at the end and work backwards and find the first index where the element fits. Okay, so it doesn't fit at index 1 because of that whole inequality disaster happened, but it's pretty clear 187 is too big to be before 10. And then I discover, okay, so 10 could go into index 0, but 187 has to be moved over. Okay, so once I've done that, B is back in sorted order. So I have to move 187 over to make space and then put 10 in. Notice how that process was the insertion process we discussed in lecture 5 for inserting into an array. And maybe we can think about that's where we get the name insertion sort from. Now I see the -5. Okay, so I'm going to start at the end and work backwards, but you could always start at the beginning and work forwards for this. So I say, well, -5 can't go here because, and I'll think about it this time, yes, because 5 is less than 187. 187 is greater than 5. Okay, so what about putting it here? Well, this isn't going to work because although 5 is less than 187, 10 is greater than -5. Okay, so then I have to go back and I try index 0. So I just walk backwards. Later in my pseudocode, I'm going to do both the walking backwards, both the test of indices and the moving elements at once. So I'll actually say, can I put -5 here? No. Okay, so free up an empty space. So I'll clear out the index before and put 187 over here. Can I put -5 here? No. Okay, so move over 10 and then free up index 0. Can I put -5 here? Yes. Okay, so then I'll just put -5 there. So I'll actually move elements over as I'm walking through the array, just so that when I get there, I'll already have an empty space waiting for me. Okay, so I have to move everything over. I put -5 in. Notice that at each step, So I look at index 0 of A and I put it in B. And then once I've seen an index 0 of A, I'm never going to see it again. I walk through each element of A in left to right order, and I only see each unsorted element once. And then once things get put into B, they may get rearranged over and over again. Consider what we did back during selection sort. During selection sort, at each step, I set one element of my sorted array, and then it never gets moved around again. But the elements in the unsorted section might get permuted over and over again as I keep swapping things. So think about that. Selection sort and insertion sort seem to have a lot in common. They're performing the same task, but in an opposite way. Instead of, for insertion sort, the unsorted array is basically visited once. I look at each unsorted element once, but then I shuffle around the sorted elements over and over. Whereas in selection sort, I fix each sorted element once, but I might permute the unsorted elements over and over. Okay, anyway, so here for the value 6, I discovered that it's supposed to go in index 1, so I push everything over. The element 225, well, quite conveniently, I can just jam it directly into the last index of B. Same thing for 226. And of course, if I'm lucky enough to have this situation, that's very fast. Not only do I not have to move anything over, I also don't have to work backwards through the array to search for a position. That's one reason I like starting at the end and working backwards. Although there's no reason why it really is any faster to do it that way. It's just convenient for me to think about it. However, although we are sometimes lucky and get to insert elements at the end, we can't expect that we'll always be that lucky. So here I want to insert -1. Okay, can't put it there, can't put it there, can't put it there, can't put it there. Okay, I can put it between the -5 and the 6. So I may have to move over. You can see this is n-1, or I guess if the size of B is k, it's k-1 items have to be moved over before I can insert the last element. And so, because this algorithm, of course, is based on the insertion operation into a sorted sequence, we can call it insertion sort. You'll notice that I've said for both selection sort and insertion sort, it's usually called that. So I'm a bit uncomfortable about coming up with canonical names for algorithms. So there are algorithms out there that have one name that everybody agrees on. And usually when those algorithms, when we have names like that, it's because the inventor of the algorithm gave the algorithm a name, like they published a paper and said, this is my algorithm called X. So Quicksort, which we'll see later, was one of those. The inventor said, this is Quicksort. Its name is Quicksort. They gave it a name that was a proper noun. Then everybody just calls it Quicksort. This algorithm here, I'm not sure who can be credited as inventing it. I think it's one of those algorithms that's so fundamental that it's sort of considered to be public domain. It's common property. So it doesn't really have a proper name because it didn't have one inventor that gave it a name. And so I call it insertion sort. I think that is the consensus of the name, but who am I to decide what to call things? Same thing with selection sort. Every algorithms textbook I've ever seen seems to call it selection sort, but I've actually had a colleague in the past that called it something else, so who knows? So keep that in mind. Occasionally you'll hear people call something by a name you're not familiar with, but it could be just as valid of a name. We get into trouble with that later in the course because we begin to encounter algorithms that are named after people. Because somebody invents an algorithm or something, they publish one, and then they don't give it a name. So people name it after the person who published it, even though they may not have actually invented it. Maybe somebody else invented it earlier and nobody read their paper. I'll talk about that when the time comes. That really irritates me because we should name things, we should be conscious in our decisions to name things. Anyway, we call this algorithm usually insertion sort. Here is some pseudocode for the iterative version of insertion sort on an array. I did this with selection sort as well. We could define it with a linked list. We could also define it recursively. It would just change the analysis, but the running time itself would actually be the same either way. So in this version, I make a new array B of size n, and that's maybe a little bit wasteful, but not asymptotically, because making a new array is just big theta of n, so I'm allowed to do it without making the running time take any longer. And then I iterate through, the first element of my sorted sequence is easy. And consider that in selection sort, it was the last element that was easy. When I got to copying over the last element in selection sort, that was easy because it was already in the right position. In insertion sort, copying the first element is easy because in the array B, if the array B has size 1, a sorted array, an array of size 1 is always considered sorted. There's that observation again. We're going to need that one at least once more during this lecture. So I just copy in the first element of A to the first element of B, and then I wander through all the remaining indices of A, and at each step I find the index K where I need to insert my value into B. So I start, as I said, I've written this to start at the end and work backwards. So I start at index K, and then I just keep walking backwards as long as the index of B that I'm looking at is too large. So in other words, that would be the situation where, let's think I'm inserting, let's do 10, 187, and I want to insert -1. Well, okay, so can I insert it at this index K? Well, no, because index K minus 1 contains a value greater than the value I'm inserting. Okay, so I move K back. Can I insert -1 here? Well, no, because K minus 1 contains a value greater than -1. Okay, can I insert the value here? Yes, although, of course, 10 is in the way. And the way I get around that is at the beginning of my process, so when I'm starting with index, in this case index 2, I say, can I put -1 here? No. Okay, so move K backwards, but as you do so, you can see on line 7 here, also move the element over. So now I move K backwards and there's already an empty space waiting for me. And I say, can I put -1 here? And the answer is no, I can't because 10 is too big, so move 10 over. So basically move the empty space down with the index K. And actually what you can observe here is that at the end of each iteration of this while loop, index K of B will be an empty space. So whenever I'm ready, I can insert the element directly into position K. And then I guess I put it there. Okay, so a couple of observations about this. Hopefully it's clear that this loop is definitely running for n operations, or big theta of n operations. And then the question is, how long does this thing take? And I think the easiest way of asserting a worst case running time here is to begin with a big O, to simply say this loop definitely, I claim, definitely does not run for any longer than n iterations. And here's how I know that. Because K, the loop counter, starts at a value I, and I is definitely less than n. So K starts at a value that's less than or equal to n, or I mean less than or equal to n minus 1, I guess, and K never ends up less than 0, which means the total number of iterations of that inner loop can't be any greater than n. And that means that if I combine the inner loop and outer loop, the total number of iterations cannot be any greater than n squared. So that's evidence, I think, that the algorithm is big O of n squared. Okay, and the slides are a bit late to the party here, but they also seem to claim that. So it's big O of n squared because the inner loop, are the slides going to tell me this? Yeah, okay. I better let them take over here. So the outer loop runs for n minus 1 iterations, that's obvious. The inner loop cannot run for longer than n iterations. And that means that combined, and I mean everything else, I guess, so this is all, okay, this isn't constant. That's actually incorrect. But this is constant, that stuff's constant, this is constant, this is constant. So those don't contribute to the n versus n squared thing. Although line 2 actually does take big O n time, that doesn't matter too much because we know we're working with an n squared for the outer and inner loops. So that means that the total running time of the algorithm cannot be greater than n squared. So it's definitely big O of n squared. Now the question is it going to be faster than that? So for selection sort, this was easy because the loops ran for the same number of iterations on all inputs. It's reasonable, though, that this loop could take a different amount of time depending on the structure of the input array. And so we have to talk now about what is a worst case input, because there could be inputs that are not worst case inputs. And so I'm going to leave that as an exercise, but it's not a very difficult one. It's actually something where just looking at the example we already did, it's sort of clear what we can do to maximize the total amount of work that gets done. And I'll scroll back over and we can skim over some examples of that. Okay, so let's take a look at this insertion here. Clearly, I don't do any work. I do very little work in the inner loop here. I just copy the next element into the first into the first position that I check. So the inner loop does no work. Versus at the end here, I have to do a whole bunch of work because I have to move everything over to make room for -1 near the beginning. So use that observation as inspiration to create your worst case input. In any event, it turns out there are worst case inputs such that the total number of iterations of both loops together is big theta of n squared. I'll even spoil the analysis, which is that you can make this inner loop over the various iterations of the outer loop require 1 iteration the first time, plus 2 the second time, plus 3 the third time, all the way up to n minus 1, just like with selection sort, which is interesting because I keep pointing out these similarities between insertion sort and selection sort. But yeah, it turns out that the way you get the n squared there is via that sum. Again, it just keeps showing up. So insertion sort's worst case is big theta of n squared. But there are cases where it can be much better than that. So for example, on this array, I won't do the exercise because I've already done too many exercises out of the slides today. On this array, it turns out that insertion sort is big theta of n. I will do a related exercise. Consider this array here. Let's do 0, 1, 2, ... n minus 3, n minus 2, n minus 1. In other words, consider an array, we'll call this one A prime, that is already sorted. And it doesn't meet the same standard of craftsmanship as the array above, unfortunately. I didn't square off all the corners, but somebody's got to get that looked at. There's a bit of a camber there. But if I try and sort this array with insertion sort, let's think about what happens. Okay, so I'll make my array, we'll call it B prime. Okay, so the 0 gets copied directly. That's a freebie. But the 1 gets copied directly. That's also a freebie because it's already in the right position. And so does the 2, and so does the ... and then so does the n minus 3, and the n minus 2, and the n minus 1. In fact, arguably, that inner loop is probably never iterating at all. And so at each step, I just copy one element in, and therefore the algorithm will be big theta of n on this input. And I want you to take a look at that array and see if you can prove the same thing about it. Because it turns out there actually are, you can classify lots of different types of array for any value of n where insertion sort is actually linear. So the version of insertion sort we just did uses two arrays. It has an array B that stores the sorted sequence. But if we think about this, I guess it's sort of clear that we shouldn't need that, because as we process each element of A, we never need to work with it again, so we can throw it away. And therefore, there's sort of this empty space in A. I'm going to scroll back to my earlier example to show that off. If we look at, let's say, this state here, where these are the remaining elements of A. All of these elements of A are irrelevant to me now, because I've already put them in my sorted sequence. And then I observe that my sorted sequence has the same size as the set of elements I just ignored. So why don't I just store my sorted sequence in the first bit of A, like selection sort? Why bother with a second array? That's a good observation, and we should see what happens if we do that. And when you go to implement insertion sort, you probably will just do it the second way, because that way you avoid allocating an extra array. There's nothing wrong with allocating extra storage. There are cases, though, where you do care about how much storage you're using, and in those cases, of course, yes, then it's better to use less. Especially if asymptotically the running time doesn't go up. There are cases later in the course where we will see that using a bunch of extra space results in a faster asymptotic running time. And in those cases, it's often better to use the extra space. Whereas, especially if it's like going from n to n squared. That is, if I have an algorithm that takes n squared time but requires only a few variables of extra space, let's say like 5 units of space, versus an algorithm that requires n running time but requires n extra space, you better believe I'm going to choose the second one. An interesting observation about space consumption is that if you need n extra space, the algorithm has to take at least n time, because allocating the space requires time. So it's sort of weird, it's illogical to think about an algorithm that takes n time but requires n squared space. That doesn't really make very much sense. Okay, but that's just an aside thought for now. What I could do is, as I said, just store the sorted sequence in the first few indices of A. Now, I do have to do a little bit of swapping around, so I suppose I do still need a place to put something temporarily while I rearrange stuff. So this is actually not necessarily true. I could do a bunch of swapping inside of A, and it would work just fine. It wouldn't change anything. But for the sake of clarity, making one extra variable really makes it easier to illustrate this. And when we talk about space consumption, in general, adding one extra variable doesn't hurt us. It's only if we add n extra of units of space that we have a problem, or log n or whatever. Okay, so what I'm going to do here is I'm just going to basically draw a line down the middle of A and say everything to the left is the sorted part, everything to the right is the unsorted part, and then over time that line is going to move forward. And then by the end of the algorithm, the entirety of the array A will be sorted. So what I do at each step is I take the element, I take it out of A, I guess conceptually, and just put it in a holding area for a minute while I arrange for it to be, an empty space to be created for it. Of course, at the beginning, it's easy because the value 187, the first element of A, is automatically the first element of B when B is empty. Okay, so at the end of iteration 1, I have one element of my array in the sorted section. Now I take 10 and I put it in my holding area. That way, if I want to, I can move the element 187 element over to make an empty space for it. Now, as I said, I actually could just move it backwards by 1, do a bunch of swaps. That would work too. You can do that way if you want. Okay, then I put 10 there. Then I put -5 in, and that lets me move everything over. So -5, I guess the slide skipped over that step, but it lets me put 187 here and 10 here, and then blank out space 0, so -5 can go there. I think you get the idea. So at each step, basically the B portion, this is the sorted portion, B now lives inside of A, and over time B gets bigger, and eventually it takes up the entire array. Okay, so other than that, it's the same as the other algorithm. I'm just combining things into one single array, which is my input sequence. I believe I advance the argument, so this is my opinion, that insertion sort and selection sort are dual. That is, that they are two sides of one coin. They are twins. They perform effectively the same operation. They leverage the same insight, which is that we can grow a sorted sequence from left to right. They just do it in the opposite way. And there's a description of what I mean with some technical language here, but basically that selection sort sweeps through the array from left to right. So if I look at the array, and I think about at iteration, if I'm at iteration I of selection sort, everything over here is in its final sorted position. There are some things over here that are not, and they might keep moving around. I might keep moving the elements in the unsorted section around as I take care of that, but everything to the left of index I, when I get to the beginning of iteration I, is locked down. It's in its final sorted position. And selection sort, therefore, walks from left to right over the array, locking in elements on the left, and then on the right, moving elements around to do its bookkeeping. Let's think about insertion sort, though. So if I think about insertion sort, at every step I, when I get to the beginning of step I, everything to the left of I is in sorted order, but it may not be in its final position. I may still have to do a bunch of swaps internally and move things around to make space. On the other hand, everything on the right remains in its original unsorted order. I never move anything around over here during insertion sort. And so I think that, in a sense, that's a mirror image of selection sort. Selection sort does its work by locking down things on the left, and insertion sort does its work by leaving everything on the right untouched and moving things around on the left. So I think that they are duals of each other. Now, that said, they're both n squared in the worst case, but insertion sort can be faster than n squared in some cases. I don't really think that changes that selection sort and insertion sort are sort of siblings. That is, they still have a lot in common. It doesn't, I mean, some of them, as with any pair of siblings, some might have different talents than others. That doesn't necessarily mean that they don't share a lot of the same genetic information or whatever. And I'm going to make the same point later about the next two algorithms that we cover, that they have lots of differences, including running time, but fundamentally they are using the same technique, approaching the same problem in the same basic way, just moving around where they do certain types of work. Now, both selection sort and insertion sort, as we've seen, can be implemented with what is called an in-place strategy, with an in-place methodology. So an algorithm is called in-place if it requires big theta of 1 extra space. That's weird. We've just applied big theta to something other than running time. So of course, we can quantify the amount of space an algorithm uses, and we can talk about that asymptotically. This algorithm, so insertion sort that we just did, does use big O of n space, but the space it uses is space that was provided from outside. You give me an array, and I use the array as scratch space. I only create big theta of 1 extra storage locations. That is, I might make a few local variables, but it's a constant number of local variables. So even if I need 10 like loop counters and swap variables, it's always going to be 10 of them. So no matter how big the array gets, there's always going to be 10. So I need big theta of 1 extra space. Versus the earlier insertion sort, where I had to make a copy of the array. And of course, the size of that copy is proportional to the size of my array. That would require big theta of n extra space. And so basically, temporary storage. Basically, an in-place algorithm for sorting can be quite helpful, especially if you don't sacrifice the running time, because think about it, if you have a computer with 64 gigabytes of memory and you have an array that's 40 gigabytes in size and you want to sort it. well, you can't really make a copy of the 40 gigabytes if you don't have enough memory for the copy. So that is one reason why having an in-place algorithm is helpful. And I mean, that's true of all applications, right? If you have a huge amount of data, you'd rather not make a copy of it. But certainly for sorting, it is quite plausible we might have a single array of data that we have enough time to sort that takes up 40 gigabytes, that takes up a huge amount of our computer's memory. I should add, though, that if you are trying to sort a 40 gigabyte array, and that 40 gigabytes is a huge number of values, I mean, I guess this could be an array of size 40, where each value is 1 gigabyte in size, assuming this is billions of elements or something. So this would be, about a billion integer elements. If you're trying to sort that, you probably should not use insertion sort or selection sort, because, 1 billion, so 10 to the 9, if we put that into an n squared algorithm, we're going to get a large number, uncomfortably large number. On the other hand, actually, an n log n algorithm for 10 to the 9 wouldn't be the worst. It would take a while, but it wouldn't take that long. You can get that done in a reasonable amount of time. Okay, out of nowhere, I suddenly want to talk about this problem. We didn't even get back to our character select screen. Just out of nowhere, it occurred to me that we should talk about, hey, how do I manipulate sorted arrays? What happens if I happen to have two small sorted arrays and I want to merge them together into one big sorted array? So I think, well, okay, if I have two small arrays that aren't sorted, I could always just merge them together and sort them. That would take, I guess, n squared time with insertion sort. I'm talking about a very specific problem, though. I have two sorted arrays, A1 and A2 are both sorted. I want to find some clever way of merging them that requires very little time. And I guess I'm hoping to leverage the fact that a sorted array has a lot of internal structure. Like, we know a lot about the way the elements should be ordered inside of a sorted array. So here's my observation. If you give me two sorted arrays and I ask a question like I did with selection sort, like, what goes in the first position of my result? Well, it's either going to be the first element in A1 or the first element in A2. In this case, it's going to be the -5. So I think, okay, let's copy that in. And then once it's in there, I can get rid of it. I can just ignore it and pretend it's not in A2. Now I ask the question, what goes here? What goes in the second position? Well, I think, well, it has to be either this or this. Because, I mean, as a thought experiment, it clearly can't be 225, because if it were, that means that when I eventually, store the 17, if it ends up like here or something, that's obviously not allowed. So clearly the next element after the -5 has to be either the -1 or the 6. And so in this case, it's the -1. So I'll just cross that off because I've already taken care of it. And I notice that at each step, it's the same question. Is it the first element of A1 or the first element of A2? And once I cross it off, I ask the same question again. But the beauty of that is the question I'm asking is actually constant time. Comparing the first element of two arrays, that's comparing two things against each other. It's always two things. It doesn't matter how long each of my arrays is, I'm only comparing two things. That's a pretty big deal. Okay, so I'm going to let the slides catch up because the animation that the slides provide is going to be way better than what I just drew. Okay, so I do -5, and then I delete the element from A2. Now, who knows what I mean by delete? I could just pretend it's not there. I could just pretend A2 starts here. Who knows? We just cross it off and then never see it again. Okay, then I do -1, then 6, then 10. And at each step, all I do is look at the beginning of each array, of the remaining elements in each array. And that's a constant time question. And then, of course, I perform a copy, which, a single copy operation is also constant time. Which means if I consider the size of my eventual array A to be n, then it sounds like the process I'm describing is actually big theta of n. It's actually a linear time operation. Okay, so I'll finish the merge. I guess I get to this position here, where there are only two elements left in A2, but there's nothing in A1. And at this point, I can actually avoid the comparisons. I just take everything here and drop it directly into the output array A. Now, a symmetric case could, of course, happen with A1 when the same thing would happen. I could run out of elements in one of my two sequences before I've run out of elements in the other. And so each step of this merge operation was constant time. It only required looking at the first element of each source array and then copying one of those elements into A. It's a little bit tedious, like it's involved, but it turns out it is actually a linear time algorithm. It's just that there's a lot of cases to consider and a lot of indexing to fiddle around with. The way I've chosen to implement this with this pseudocode here is I have, when we talk about deleting an element from A1 or A2, I left that vague because how we do that depends on the context. Basically, all I do really is I just keep an index into each array that refers to where sort of my idea of the beginning of the sequence. So index 1 is, in my opinion, the beginning of A1. Everything before index 1 I pretend isn't there. Same thing with index 2. And I also keep an index which I call index out to refer to the next available position in A. And so I have this while loop. So yeah, I start them all at 0. So I'm copying every element from A1 and A2. And then I have this while loop, and this loop covers the case where there are still elements left in both arrays. Well, index 1 is less than the length of A1, and index 2 is less than the length of A2. So both arrays have at least one element left. If that's the case, I compare the element at the beginning of each array. So I look at index 1 of A1 and index 2 of A2, and I ask which one is less. If A1 has a smaller element, then I copy that element into A, and I increment the appropriate index. Otherwise, I copy the element from A2 into A, and I increment that index, and then I increment the index into A. Now, at the end of this while loop, that'll correspond to the case where one of the two sequences has run out of elements. So that would be this situation here, where there's still stuff left in A2, but there's nothing left in A1, or vice versa. It'll always be one of those two cases only. There will never be a case where there's stuff left in both of them, because then I'd still be inside the while loop. But I can save myself a bit of time and write these two copy statements in my pseudocode to cover both as if they could happen together. But to be clear, only one of these will ever happen on a given run of the algorithm. And all I do there is I just copy everything else left over in either sequence directly into A. And I argue that this whole process takes big theta of n time. And the easiest way to make that argument, I think, is to point out that at each step of this, one element is getting copied into A. And so if I count the number of total copies, the running time of this sequence of things has to be proportional to the total number of elements copied into A. And that means that because we know that A has size n, or I mean if I define this number to be n, A has size n, and so this whole thing must take big theta of n time. Because the number of operations is proportional to the number of copies into A. If I look at, all the work being done, it all hinges on every iteration of this loop, I'm copying something into A, and every operation in this block copy, which I didn't expand out because I think we can agree that it's possible to copy from one sequence to another, everything in that block copy copies one element at a time into A. So we can assume that it's big theta of n. And so this is just going to expand on what I just said. But basically, this first loop runs for at most this number of iterations, but we expect it'll actually run for fewer than that. If I want to do a very loose analysis, and so I'm going to again call this number n, I could just say, look, this is definitely less than or equal to n, and this is also less than or equal to n, and this is also less than or equal to n, so the whole thing is less than or equal to 3n. So that's obviously big theta of n. It's actually tighter than that. It actually turns out that it's going to be less than or equal to some constant times n, just to represent the amount of work being done by the indexing and copy operations. Each step of all of these, I'm only copying into each position of A once. And so in any event, this algorithm here, this merge algorithm, is linear. So if I have two arrays of one size and I want to make one big array out of them and both input arrays are sorted, I can do that. I can merge them into one big output array in linear time. And now I begin to wonder where this might come in handy. And I remember that observation from earlier that if I have an array of size 1, an array of size 1 is always sorted. So it's very easy to come up with arrays of size 1 that are sorted. And if I want to merge them together, I can merge them into an array of size 2. Now, I mean, that's possible whether or not I had this merge algorithm, but bear with me. So suppose I have arrays of size 2. Well, now I can make them into an array of size 4 with my merge algorithm, and I can go from size 4 to size 8. And I begin to wonder whether I could use this as the basis for a sorting algorithm. Oh, and there's our character select screen just in time. I wonder which one we're going to okay, it's going to be merge sort. Let's talk about merge sort. So if I just repeatedly merge my arrays, so if I take any input array, so unsorted array, I break it up into tiny pieces, so pieces of size 1, and then I merge them together, I'm merging arrays of size 1, and so of course they're sorted, and I could use my merge algorithm to merge them into an assorted array of size 2. I could take arrays of size 2 and merge them into arrays of size 4, and I could keep doing this until I have my entire original array again. So one step of that process, give me some array A. I'm going to break it in half, more or less. So to be very careful here, obviously, n might not be divisible by 2. So I'm going to say n1 is equal to n over 2 and then take the floor. n2 is equal to this number. So actually, n2, you can think about this, is actually the ceiling of n over 2. But to make it really clear that there's nothing getting lost, I've written it as n minus n1. So I break my array A in half into two pieces of more or less equal size. And I haven't explained how I do that because I think it's pretty, you can do it however you want, but probably the easiest way is just to put the first half of elements into A1 and the second half into A2. I then recursively sort A1 and A2. And then I use my merge algorithm to merge them back together. And the result, because of course the work is being done by the merge step here, is called merge sort. We could call it merge sort with a space, like we called selection sort or insertion sort, because selection sort and insertion sort are sort of descriptions of the algorithm. It's a sorting by selection or sorting by insertion. And merge sort is sorting by merge. But it is true, over the years I've really tried to always say merge sort with a space, but I've given up on that. It is true that I generally just write merge sort as as a proper noun, as a made-up word. And that's because also its sibling, which is called Quicksort, has to be named with one word for reasons I'll come back to in a few minutes. So I'm going to call it both of these things. I think I've settled on mostly using this word here. It turns out that merge sort was invented by this guy. So you can't get through a computer science course without seeing him at least once. That seems to be a law of the universe. John von Neumann was so prolific in so many different fields that it's very hard to get away from John von Neumann. But in computer science especially, you really have no choice but to see this guy's picture every now and then in every course you take. So if algorithms aren't your cup of tea, well, maybe you might enjoy taking a computer architecture course. But if you take a computer architecture course, I'll bet that I give it maybe one lecture before you start talking about von Neumann architectures, because, he was involved with those as well. So merge sort is generally credited to von Neumann in 1945, and I'm not saying that to make it sound like I'm skeptical. I believe that he did invent it. It's just that it's harder, the paper trail is sort of harder than it would be for a more modern algorithm where people probably publish it in a journal or something. So John von Neumann invented merge sort. It's also neat because this was at the dawn of the era of programming computers. So merge sort arguably might have been one of the very first computer programs as we currently know it. Now, computer programming goes back to probably the late 1800s or something, depending on how you define a computer, but the programming of electronic digital computers certainly can't have happened much earlier than this, although sometimes there are examples where it did. So maybe in the 1930s, there were primitive or prototypical computers that could have been programmed in some sense, but the modern idea of a programmable computer seemed to arise sometime in the 1940s. Often this machine, ENIAC or ENIAC, is considered to be the first all-purpose digital electronic programmable computer. And it was originally designed to compute, I think, like artillery firing tables or something. So it was designed for calculations of this was during the Second World War, calculations for artillery. And I guess von Neumann, so strangely, not only did von Neumann invent merge sort, but he was actually sort of responsible for this computer getting put to one of its first uses. Although this was designed for artillery tables, von Neumann found out about it, and at the time von Neumann was involved with the Manhattan Project, which would be the development of the atomic bomb. And it ended up that the first actual use of ENIAC was for calculations related to simulations of atomic explosions because of apparently von Neumann's involvement. Among other things, though, von Neumann also invented merge sort. So hopefully that's enough of an example to show that von Neumann was doing so much stuff that it's really hard to pin him down to just one achievement at a time. And actually, so we should observe here that what this means is not only did he invent merge sort, but he was actually sort of responsible for one of the first uses of a programmable digital computer. Additionally, so von Neumann is often considered to be one of these great figures in science along the lines of like Euler or Gauss because of how many different contributions he made to so many different areas. Like I would like to say, hey, von Neumann was a pioneer of computer science who also did some neat stuff in economics and math and physics and statistics. But you could take a physics course where somebody would tell you, hey, von Neumann was a great physicist. Yeah, sure, he dabbled in computer science. Everybody has to have a hobby on the side, but he was a physicist. He made so many fundamental contributions in all of these areas that they claim him as one of their own in each of them. In any event, he invented merge sort, although at the end of the day, I'm sure if you read a biography of von Neumann, that might get mentioned like once. He did a lot of other really important things as well. Okay, so there is this course's obligatory mention of John von Neumann. So let's talk about merge sort. At each step, I split my input array into two approximately equally sized pieces. And it is significant that both pieces have size about n over 2, because later we're going to try and get rid of floors and ceilings in a recurrence. Then I take the small arrays and I sort them recursively. And the idea here is if I go up and look at my base case, if I keep splitting arrays over and over again, eventually they're going to have size 1. And an array of size 1 is already sorted, so merge sort doesn't have to do any work. It just returns. Once I have my two sorted subarrays, A1 and A2, I then call my linear time merge function to merge them back together. Now, I haven't written this as a function call because the linear time merge algorithm, I'll go back to it, it actually behaves as if it returns an array, like it makes a new array and returns it. That doesn't quite fit the pattern that I'm using here, where I'm actually merging them back into the original input array. So just to avoid having to deal with those semantics, this is using the same linear time merge algorithm, although we might have to tailor the syntax of it a little bit to this case. So in any event, this I can expect if n is the length of my array A, this step is definitely big theta of n. This step is definitely big theta of n because splitting an array in half is relatively easy. This is constant and all this base case stuff is also constant. And of course, what I have to do, because I'm making recursive calls, is instead of just waving my hands and saying, wow, it looks like this algorithm is fast, I'm going to need a recurrence. So here it is. The worst case running time of merge sort we could model by this recurrence. And I've already made one simplification, which I think is justified, which is technically the recursive calls that I'm doing are, I'm doing this. It's t of n1 plus t of n2 plus some stuff. So I'll just define two constants to absorb all of the remaining stuff. So c1n plus c2 would be all of the linear time stuff happening with splits and merges. Okay, but what about n1 and n2? Okay, so I know that n1 is the floor of n over 2. And I know that n2 is n minus n1. I said a minute ago that it's reasonably clear that that's actually the ceiling of n over 2. And now what I can do is say, okay, so the floor of n over 2 is less than or equal to the ceiling of n over 2. And they're so close together that I'm just going to bundle them both together and say, look, we're just doing 2 of the ceiling. And it's true that that recurrence might be a little bit off. It'll be off above, so I'm actually adding, it's a bit generous about the running time, but we've seen before that we actually have the option of taking reasonable liberties with recurrences, as long as when we finally get the closed form, when we finally figure out the big theta expression, as long as that's one of our usual suspects, so n or n log n or a polynomial, then it's fine. If it's something really bizarre, we may need to go back and check over our assumptions. But I think this is something I can get away with because this algorithm does feel like it's going to come somewhere between n and n squared. How do I know that? Well, I think that we can't sort an array in any better than n operations. That wouldn't make any sense. And also, I think it's going to be better than n squared. Let's just say I have a hunch. Okay, so exercise. Because we do not want to belabor this lecture with too much minute details of recurrences, go right ahead and feel free to solve that recurrence, maybe use repeated substitution and prove a closed form. You will discover that in fact t of n is big theta of n log n. Now, if you don't want to solve it yourself and you feel like you're owed an explanation, don't worry, it exists. Go back to the recurrence relations lecture and take a look at that. You will find that in fact I actually did recurrences of this exact form in advance of knowing I was going to need to talk about merge sort. So we actually do have on the record evidence that this is big theta of n log n. Now, merge sort is an example of a particular algorithm design style called divide and conquer. And just to be clear, yes, that's a clever sort of cute name, and no, I did not make that up. I'm a serious person. I only call this divide and conquer because that's what everybody calls it. So I'm going to use that name. Just because it's clever doesn't mean that I think that I'm being clever by saying it. So the idea behind merge sort is I take this big input and I split it into two disjoint pieces, so two non-overlapping smaller versions of the same problem. And a divide and conquer algorithm is one that somehow uses that methodology to save tons of work. One way that we can think about ourselves saving work here is consider that whatever I do, if I sort this smaller array, even by any method I want, not just by merge sort, if I sort the smaller array by merge sort, I never compare the value 225 against -5, for example, because they're in separate arrays. I sort this array independently of this array. And I can think about, if I did selection sort on this, I might actually end up comparing together -5 with, I guess I would compare it certainly with 6. With insertion sort, I might compare -5 to 225. And those comparisons, if I can avoid them, might save me time. The idea behind the divide and conquer pattern is that by splitting the array into two independent pieces, so two pieces that are not overlapping, I'm definitely reducing it down into two problems of size n/2. And then, once I solve those two problems, taking the result, so taking two sorted arrays of size n/2 and merging them back together, hopefully by then there's a more of a sense of order to the data that would allow me to save work. And so, as I said, when I sort the two subarrays, I never compare 225 to -5, for example. I might do that in insertion sort, and I may do that in some cases in selection sort. If I take a look at merging my subarrays, notice that when I make up my sorted array, I compare -5 to 6, and then I choose -5. And notice that that means it's impossible that I ever compare 225 to -5. And that's the advantage I'm trying to exploit. It's the idea that by solving these problems recursively, I can make it so that when I come back from recursion, the operations that I do can exploit the greater sense of order and avoid doing work that might be redundant, that might be useless. And so that's where I'm getting this advantage. In this case, so merge sort is one of many examples of divide and conquer algorithms. Much later, we're going to talk about alternatives to this. So it's very tempting. Once you learn about divide and conquer as a strategy, you pretty much want to use it for everything. Like whenever that can be applied to a problem, it yields pretty good benefits generally. And that means you try to apply it to everything, but you can't always do it. Often there aren't problems that can be broken into pieces as cleanly as this. So here I could break an array into two separate disjoint pieces, solve the problem separately, and then reconstruct the result. In a lot of problems that we're going to see in the future, we don't have that ability. We can break the problems into smaller versions of itself, but not versions that aren't overlapping. So there are cases where we can't do fully divide and conquer. We end up with overlapping subproblems. And I'll have a whole bunch to say about that, but not just yet. For today, we're just talking about divide and conquer. And so basically, because we did this divide and conquer strategy, when we get to the merge step, we can exploit our linear time merge, which leverages the increased structure of these sorted subarrays. It's often the case, this is just a rule of thumb, this is just sort of life advice, because divide and conquer algorithms generally involve some kind of recursive partitioning, so breaking the input into pieces, generally speaking breaking it in half, because computer scientists like using powers of 2, because if I want to cut something into pieces, I could cut it into 5 pieces, but why not just use 2 pieces? Hold that thought. In 2 lectures, I'll give you a reason to cut things into pieces of size 5. But because of that, it's often the case, whether you break it into 2 pieces or 5 pieces or 7 pieces, you often find that running times involve log n somehow. They may not be n log n particularly, but you often get a running time expression that has a log term somewhere in it. So even if the running time is n squared for some algorithms, you might end up noticing in the expansion of the running time there's some log n showing up, which reflects the recursive partitioning. And so often you can work backwards from that and say, if somebody gives you an algorithm and says this algorithm is n log n, you can wonder, is it because it's a divide and conquer algorithm? Now let's talk about what exactly happened with merge sort and its division and merge phases. So the divide phase in merge sort is really simple. All I do is cut the array in half. And there are lots of ways of doing that, but for arrays, it just makes sense to take the first half goes in one set and the second half goes in another. For linked lists, strangely, it can actually often be easier to simply divide them up one by one in alternating sets. So I could put this in sublist A, this in sublist B, this in sublist A, this in sublist B, whatever. In any event, dividing the array in half is very easy. It requires a very simple single pass over the array where I just toss things into two buckets. buckets, pretty much. And so the divide phase is really simple, whereas, of course, the merge phase is that linear time merge algorithm that is a bit more complicated. Let's talk about this, though. Suppose I decide to do a little bit more work during my divide phase. And this is a thought experiment because we're going to see it doesn't generalize. But suppose that instead of dividing the array simply right down the middle, I just put one half over there and one half over there. Suppose I'm working with this different array, and I decide to break it up into into a subarray only of the negative elements and a subarray only of the positive elements. Okay, so doing that, performing that split, requires a little bit more work than I had to do before. Not much, but a little bit. Because at each step I have to ask, is this element negative or positive? And then toss it in the appropriate bucket based on whether it's negative or positive. Okay, but bear with me. Suppose that I do that. Suppose I break it up into two arrays where one of them is only the negative values and one of them is only the positive values. And now I recursively sort both of these two arrays. And I want to merge them back together. How can I do that merge? I mean, I could do it with my merge algorithm, but do I need my merge algorithm? No, because I know that everything over here, everything over on the left is less than everything on the right, which means in this situation, my merge algorithm is really simple. All I do is list everything in the left and then list everything on the right, and I'm done. I've merged them together. I have a really simple merge algorithm. It's still linear time. My earlier algorithm was also linear time, but this one is a much simpler linear time algorithm. And I wonder, maybe this could give rise to a sorting algorithm on its own. Now, of course, it can't, with this negative-positive split, that doesn't quite work for us because, like what if the array has no negative or no positive elements? So in this example, my splitting process was non-trivial. I actually had to do some work while splitting. I had to ask the question, is this element negative or is this element positive? But the merge process was absolutely trivial. I just concatenate two sequences. And this is, in a sense, a dual to the behavior of merge sort. Merge sort has an easy split, but a little bit more of an involved merge. This process was a more complicated split, but a very, very simple merge. The problem with this, of course, is that it doesn't generalize. So if I have this array here, which contains no negative elements, then what do I put on the left? Nothing. Oh, and that's really scary because now I've got this array on the right that's the same array I started with. So if I recurse, I'm just recursing infinitely because I'm going to keep trying to sort the same array over. Okay, so that's not going to work. I can't just split by sign. Oh, there's the character select screen. Okay, it looks like it's going to happen. It looks like we're about to learn about Quicksort. So how about this? Instead of splitting according to sign, because that doesn't generalize, well, maybe I could exploit the elements of the array to tell me something about the array. What if I just choose an element of the array, like the number 17, and I use that to govern my split? So I make a list of things, we'll call it L, that are less than 17. I make a list of things, we'll call it G, that are greater than 17. And in the middle, I have 17 itself. We'll call the element that I use for this purpose P. It's possible maybe there's more than one thing in this list in the middle, if 17 appears more than once. I'll come back to that in a minute. But what I've done here is a basic partitioning step that just uses an element to govern the partitioning, and I've chosen the first element. I don't have to do that. And then I walk through my array from left to right. I compare each element to P, and I just toss it into one of two groups, or in the middle, I guess, depending on its value relative to P. So if I choose P to be the first element, I end up with two equally sized subarrays and at least one thing in the middle. Now, having at least one thing in the middle is nice because it guarantees me that even if I'm really unlucky, the subarrays will always be smaller than what I started with. I'll always make at least a little bit of progress towards having a sorted array. Then I recursively sort the two subarrays. The thing in the middle does not need to be recursively sorted because it's just 17. And then I just mash all three of them together. And of course, that's very simple. I just concatenate all three of them. An interesting observation here is that to concatenate the three arrays, I have to iterate over all three of them. But if I actually were working with linked lists at this point, as we know, concatenating linked lists is constant time. I just attach the end of one thing to the beginning of the next. And so this merge step is even easier if I happen to be using linked lists. Although, as I said at the beginning, it turns out it doesn't make the algorithm overall any faster asymptotically because the hard part of the algorithm isn't that. I mean, the split being a bit faster is nice, but it doesn't actually make the algorithm asymptotically any faster. Typically, we call the element that I use to govern the splitting process the pivot. That's why I called it P earlier. And once we select the pivot, because you could argue that we have a lot of options for which pivot to choose, once I select it, the process of splitting is just a simple linear time binning operation, basically. You take each thing and throw it into a bucket depending on whether it's less than or greater than my pivot P. Now, if I choose the first element of my array as the pivot, well, that's an easy choice. I mean, it's easy to choose the first element. The problem is, how do I know the first element is a good representative, sort of in the middle of the sequence, right? So if I choose the number 225, well, we might have a whole ton of things that show up over to the left, a whole ton of things that show up in my array L, and very few things that show up in my array G. That's a bit of a hazard of this approach. It's also tough because at the point when I do my splitting, at the very beginning of the algorithm, I don't know anything about my array. Unlike in merge sort, where the split is easy and I don't care about the array, by the time I do the work in the merge step, my arrays have a lot of structure. In the split step of quicksort, the array doesn't have any structure at all. It's just whatever was in the unsorted sequence. A quick note, I alluded to this earlier, but it could be possible that the array contains duplicates, and therefore that the pivot itself appears more than once, and that's fine. Really what I'm doing is making 3 subsequences. I'm making a sequence of things less than the pivot, a sequence of things greater than the pivot, and a sequence in the middle of things equal to the pivot. Now, in certain cases, but not in general, and I'll leave it to you to think about why this doesn't apply in general, in certain cases, you don't actually have to store E explicitly. You can just say, look, there's 225, there's, 3 of them in there. Just keep track of how many of them there are. Don't actually make a whole list. That doesn't work in general because we're not always sorting lists of integers. And so we're not always allowed to assume that all of the items in E are actually truly equal. They only compare as equal. They might be distinct, so it might matter that I have all of them separately. That's why I'm going to make a sequence E. And so if I recursively apply this process, I choose a pivot, let's say the first element, I divide the array into 3 pieces based on the pivot, recursively sort the pieces, and then jam them all back together, I get an algorithm called Quicksort. Notice how this is not quick sort, it's Quicksort. That's its name. Just because it's named Quicksort doesn't mean that it's quick. In fact, we're going to see that it is actually not quick. So remember, Quicksort, and in general, don't fall for the marketing. Because just calling something, giving it a cool name, doesn't mean that it actually is going to have good performance. So that's important to understand. However, that is a proper name that it was given. That's its actual name, so that's what we're going to call it. Here's some pseudocode for Quicksort. Like merge sort, it's recursive. And my base case is simply, if you hand me an array that is size 1, or unfortunately, I could actually have a case where it's size 0, well, then it's already sorted, so I'm done. So that's easy. Otherwise, I choose a pivot value. That's oddly vague. Okay, I choose a pivot value somehow, and then once I have the pivot, I create 3 empty sequences. Here is my partitioning step. I just look at every element in my sequence S. I add it to either L or G, or if it's equal to the pivot, I add it to E. I then recursively sort L and G. There's no need to recursively sort E, obviously, and then I concatenate them all back together to get S. So the merge step is easy. The partitioning step is actually pretty easy too, frankly. It's way easier than the linear time merge algorithm that merge sort uses. And then I have my 2 recursive calls. Okay, so I represent L, E, and G with subsequences of some kind. They could be lists, they could be arrays, who cares? It actually, some things are easier on lists than arrays, but ultimately the running time won't be any different. And in any event, whether I use lists or arrays, the split and merge steps, these whole things are all linear time. So just like with merge sort, we can avoid having to do a high level, or a low level detail-oriented analysis of these because it's very clear we can do this in linear time. Now, line 6 was left vague, and that was deliberate because arguably the pivot can be selected in lots of ways. I could choose the first element as the pivot, I could choose the last element as the pivot, I could choose a random element as the pivot. I could even do something more complicated than that. We're going to, in this course, assume that if the algorithm is just called quicksort, so to be considered an ordinary quicksort variant, the pivot selection rule is expected to be something very simple, something like choosing the first element, the last element, or a randomly selected element, or the 7th element, or whatever you want, but it has to be something that we can do in constant time. For our analysis in a minute, it'll become clear that even if this step does take big theta of n time, which means it takes about as long as the split or merge step, that doesn't actually change anything about the ultimate running time. The issue is that the longer you take to select a pivot, the slower the algorithm is going to be overall, and that Quicksort has a couple of other disadvantages where if you begin choosing pivots via complicated rules, you're going to outweigh any real advantage of using Quicksort. And so it does turn out that in practice, the pivot selection rule is something very simple. So first element, last element, random element. So what's the worst case running time of Quicksort? Well, as I said a minute ago, the split step is big theta of n. That's pretty easy. And the merge step, similarly, is very simple, and that can be done in big theta of n operations. We will assume for our analysis, as I said, that the pivot selection rule, we don't want to analyze just one of them because that would require too many cases. So instead we'll just say, look, if you have a pivot selection rule, we're going to assume it's linear at worst. So usually it's constant, but even if it's linear, it doesn't change anything because other parts of the algorithm are already linear. And so what we're going to do is, as usual, avoid doing operation counting. We're going to assume that the number of operations for the base case is just some constant CB, and then the number of operations excluding the recursive calls for the non-base cases is this, C1n plus C2, so some linear function of n. Well, then my recurrence looks like this. So unlike the merge sort case, I do actually have to keep both of these extra calls to t in separately because, of course, the size of L and the size of G are not guaranteed to be that similar to each other. We've already seen cases where the size of L and the size of G could be equal, but we've also seen cases where they're going to be way different. So I guess I have to analyze the recurrence in this form. I can't eliminate cases unless I want to talk about special cases separately. So I guess the question is, we want to know the worst case running time. So I want to know what is the largest that I can make this for a particular value of n. And so the question then comes down to pretty much, well, I mean, I have to do something with these two recursive calls. So what division of values between L and G gives me the worst running time? Well, I guess there are two extremes, which is pretty much L and G can be the same size, or L and G can have completely different sizes. So the first one is, suppose it's the same size. Okay, well, if L and G have about the same size, the maximum size is this, the floor of n over 2, not the ceiling, because we know that by the time we get into L and G, at least one element is missing. Because there are only n minus 1 elements to put into L and G in the worst case, because at least one element gets stored in E, which is the pivot. So that means it's the floor of n over 2 things end up in L and G if they are as balanced as possible. Now, we already saw basically this recurrence. This is actually a little bit better than the merge sort recurrence, but it's going to be n log n. So if elements get split evenly between L and G, then we get an n log n running time. The question is that the worst case? Is it any better to do it this way than if we split them unevenly? Now, intuitively, I think it's probably clear to you as it is to me that an uneven split is probably going to be worse, and it turns out that it is. So in the worst case, we make a really bad choice of pivot. And the problem here is that it's not clear that that choice was bad until we're done partitioning. If I look at the first element, I can't tell in advance if it's going to be a bad choice. So I could do the partition and discover it's a bad choice, and then what do? Try a different pivot and start again? Well, I mean, I guess I could do that, but it would eat up a lot of time to keep doing that. So in general, as I said, to be regular quicksort, we do one partitioning step. And if we made a bad pivot choice, well, better luck next time. So in the worst case, I choose a pivot that does go in E, but nothing goes in one of the two subarrays. So let's say, for the sake of keeping things simple, that everything goes in L. Because, I mean, if everything goes in G, it's the same case, but sort of a mirror image. So that means that NL is going to be n minus 1, and NG is just going to be 0. And that's probably going to be nasty, because the whole point of divide and conquer is divide. And this didn't really do much division. So in the case where everything ends up in L, or symmetrically where it all ends up in G, it's going to be the same either way, the recurrence reduces down to this. So this is NL, n minus 1, and this is NG, which is 0. Okay, so I can now eliminate the T0 pretty easily. That's just going to be CB. Okay, so that's where I got the CB from. And then I have this, which is a recurrence in a pretty normal looking form for us that, we can't use the master theorem on it, but we can solve it with repeated substitution. So I went and did that, and I got this closed form. And you're welcome to go right ahead and try it yourself, and you'll probably get the same closed form. A couple of observations. One is that in the closed form, I get this summation here. And boy, have we seen this one a lot recently. Okay, so what is this? This is going to be n minus 0, n minus 1, n minus 2, n minus... Okay, wait a minute. I know what this is. It's going to end up just being the reversal of 1 plus 2 plus 3 plus 4 up to n. There it is. We know what that looks like. So I'm at first just going to replace it with this summation just to make it look easier, or just to simplify it a little bit. But it is just the sum of 1 plus 2 plus 3 up to n. Okay, so here is my unproven closed form. And if you want, you're welcome to go right ahead and prove that. It's actually probably easier to prove with the summation still in there. So prove that in the case where your recurrence reduces to this thing, you end up getting that this closed form is correct. You don't actually have to derive the closed form yourself to write the proof. And the proof isn't so bad, but we've got other things to do today. So go right ahead and prove that if you want practice. And I'll take that. And as usual, by assigning it as an exercise, I have made it something that I can now claim is true. So proceeding from there, I have my closed form, which I'm now going to regard as proven. I can then replace this summation with our usual closed form for the summation. And we can now see that this is going to be n squared. I mean, it's because of this. And this was also, by the way, this summation also made selection sort n squared earlier, and arguably insertion sort. So what this is telling us is that in the event where every pivot selection was bad, so every pivot selection resulted in everything ending up in G or everything ending up in L, quicksort is going to be big theta of n squared. And you could think, well, that's not so likely, right? Well, maybe it isn't, but we're talking about the worst case. And in the worst case, yeah, I make the worst possible choices at every single step. And that means that quicksort we have to regard as being an n squared algorithm. So we can think of actual worst case inputs based on that. So of course, the structure of a worst case input depends on the pivot rule that you're using. Because if I always choose the last element, then I have to maybe engineer a sequence of my array elements to sort of take advantage of the last element always being a poor choice. So suppose that I choose my first element as my pivot. Well, then if I hand you an array that's already in sorted order, like that one, well, the first step, this is your pivot, and everything else goes in G. At the second step, that's your pivot, everything else goes in G. The third step, that's your, and so on. And you can see how at each step, everything's going in one subarray, and so I'm not getting any of the benefits of the divide and conquer strategy. The same thing actually holds if I have a reverse sorted array as well. So here, the first step, n is the pivot, everything goes in L. Second step, n minus 1 is the pivot, everything goes in L, and so on. I could even make mixtures of these. So this here would also work. 1, n, 2, n minus 1, 3, n minus 2. At the first step, everything goes in G. At the second step, everything goes in L, and so on. I hope that's enough examples to demonstrate that it's not like there's just one problem that we're dealing with here. So, I mean, if it were true that quicksort is terrible on sorted arrays, but great on everything else, well, you could just have a pre-processing phase that looked at the array and decided if it's already sorted, and then you could cut out the worst case. It's not that simple. It turns out that you can come up with tons and tons of worst case inputs that exploit whatever pivot rule you make up. Additionally, it's also pretty common for people to hear about quicksort and think, oh, well, that's why you don't choose the first element as a pivot. Just choose something a little bit more clever, like the element in the middle of the array. Well, yeah, but even in that case, you could construct a worst case input. It would require a bit more thinking, but you could still do it. It doesn't matter where the element is. If you're always selecting the same element, or in general, if your element is selected by any deterministic process, you could reverse engineer an array where every single selection results in the worst possible pivot choice. And that means that quicksort is n squared in the worst case. And actually, one more note about that. It turns out that this will be n squared even if only half of all pivot choices are bad. If you can guarantee that 50% of pivots that you choose are the worst possible choice, that's actually enough to make quicksort n squared. And you could demonstrate that via the recurrence, but we're not going to do that in this lecture. And so it isn't as simple as simply coming up with a clever pivot selection rule, unfortunately. We need something very complicated in our pivot selection rule to ensure that at every step we're dividing elements reasonably well between L and G. I will come back to this problem, though, in a couple of lectures. So in any event, if you give me a simple pivot selection rule, I could give you a worst case input that results in n squared behavior. There are no constant time pivot selection rules known that facilitate a worst case running time of n log n. That's not to say that they can't exist, but simply that nobody's discovered one yet. And there is enough evidence, I think, that it's unlikely that one exists. I don't know, I haven't looked up whether there might be pivot rules out there that allow you to do better than n squared, but just not n log n. Like maybe there's one that gives you n to the 1.9 or something. But for our purposes, we care about, is Quicksort as good as merge sort? We know that merge sort is n log n. Can I get a worst case running time of n log n with Quicksort? And the answer is apparently no. But let's try and give Quicksort the benefit of a doubt. So I'm going to go back to that timing experiment that I talked about way back in lecture 1. I've added one extra series to it though, which is to talk about Quicksort with a different choice of pivoting rule, one that brings in randomness, something that we haven't really talked about much in this course yet, and we're not going to talk about much for quite a while. But I want to show off that Quicksort does have benefits. So if I run Quicksort on randomly generated input, and recall that back in lecture 1 we talked about timing experiments, and we know that we can't generalize from them, and we also saw rigged ones, but this one that we saw, this was not a rigged experiment. This was a legitimate experiment using implementations of Quicksort and merge sort that I wrote in C++, and I claim they were competently implemented. You can judge for yourself, I guess. What we can see is if I run Quicksort and merge sort on randomly generated input arrays, well, if I generate my array randomly, what are the odds that every time I choose a pivot, it's the worst possible choice? Probably very low. So a randomly selected array is unlikely to have the bad behavior that breaks Quicksort. And as a result, on those randomly generated arrays, Quicksort actually comes in, if I choose the pivot as the first element, it comes in respectably faster than merge sort. So it's not asymptotically faster, it's probably about n log n, but because the split and merge steps of Quicksort are pretty quick, like they are relatively simple and streamlined, Quicksort is able to get an advantage on those arrays of random data. I've also tried writing an implementation of the same Quicksort algorithm, but I've changed the pivot selection rule not to choose the first element, but to select a random index using a random number generator and then use that. And actually, rather to my surprise, it came in quite a bit slower than merge sort. I mean, quite a bit in the sense of absolute time, not in an asymptotic sense. And because I know that these two are the same code except for pivot selection, it's sort of clear where that slowdown is coming from. It's that I used a random number generator that apparently was rather slow, and I probably didn't need to do that. So I was working in C++, and I chose the fanciest random number generator in the library, which I think is called, it's the Mersenne Twister, which I think is called something like this in the library. And I suspect that this is actually a great deal more complicated as far as a random number generator than we need for this purpose. There are reasons you might want an advanced one, but I didn't really need one, although I did use one, and I ran the experiment, and I'm going to show the results one way or the other. So that's why it's a bit slower. With a more clever random number generator, one that's faster, you probably could have gotten better performance than this. That actually isn't the main point I want to make, but I wanted to observe that it is a bit slower, probably because of the random number generator choice, although having it be a little bit slower than the first element case might be worth it if for the insurance policy that I'm getting, which is if I choose a randomly selected element as my pivot, how likely is it that no matter what array you give me, that I always choose the worst possible thing? Pretty unlikely. The probability is extremely low. However, it is still possible, and that's why we can't use randomly selected pivot selection as an argument that Quicksort is n squared, n log n in the worst case. Because in the worst case, I'm incredibly unlucky and all of my randomly selected pivots are really bad. Okay, so in general, the Quicksort, okay, actually Quicksort generally outperforms merge sort on randomly selected inputs if I don't use a random pivot, so I don't have the extra overhead of my random number generator. If I switch over to sorted arrays, we saw the same thing we saw back in lecture 1, which is that Quicksort with the deterministic pivot rule explodes. So whereas it's actually impossible to distinguish at this scale, it turns out that merge sort and random pivot Quicksort are basically just down where they were before. They're probably sitting somewhere around this level, so 0.08. Versus deterministic first element pivot Quicksort is up here at something like 290 seconds. That's obviously a disaster. And as I said back in lecture 1, this is why we do worst case analysis, because I need to know about the risk that I'm taking by choosing Quicksort. What if my pivot choices just happen to be really bad? What if somebody feeds me an array that happens to contain just this wrong sequence of values for my pivot rule? If I use a randomly selected pivot, I'm insulating against that to a large extent. It's extremely unlikely that my randomly selected pivots are always bad, but it is possible. It may not be probable, but it is possible. So the worst case input, or the worst case running time is still n squared, even though I'm unlikely to see it. It is worth noticing, though, that because of the behavior of this, when I choose a random element, and the behavior on random arrays in general, overall, the odds that a particular array, even if I'm choosing the first element as a pivot, if I randomly select a possible input, the odds that it's a worst case input are very, very low. On average, Quicksort does have n log n performance on a typical input. However, there are these n squared inputs out there, and there are a non-trivial number of them, and so for worst case analysis, I need to make note of that. This idea of characterizing the performance on an average input is, we call this the expected case running time. And we're going to talk a bit about that, but not in this lecture. We're going to talk about that in a future lecture where it's a topic more relevant to the application we're discussing. And so, as I said, it's useful to know the expected case running time, but it's generally also very important to have the worst case running time so you know what you're getting yourself into if everything that could go wrong goes wrong. All right, so there's our coverage of 4 algorithms, 2 little families of algorithms, 2 dual cases, insertion sort and selection sort, merge sort and quicksort. And we can now, we haven't talked about what the word stable means. I'll bring that up in the next lecture, where we will also talk about the alternatives to comparison-based sorting. But we can see here that all of the algorithms on our list, so all of our selection-based algorithms, have an implementation that can be done in place, that is, without any extra space beyond a few variables. Merge sort and quicksort, by their normal design, do require big theta of n extra space, and that's actually over all the recursive calls. If we're clever, there's a way of only needing big theta of n extra space overall for the entire algorithm. There are ways to implement both quicksort and merge sort that claim to be in-place implementations, but they're distinct enough from the basic version that they're not generally considered to be the same algorithm. That is, a so-called in-place merge sort has a worst-case running time that's a tiny bit different than this and can require less space, but it's different enough from traditional merge sort that we don't consider it to be the same algorithm. It's considered to be a sort of advanced variant. And therefore, for our purposes, we will consider both of these algorithms to be not in-place algorithms. Okay, so next time we're going to talk about alternatives to comparison-based sorting. So what happens if you are allowed to use other properties of your data besides simply, is this less than that? And then sometime in the future, once we know about heaps, we'll talk about heap sort. Although by then, we'll sort of be over sorting. But we will get there and we will talk about that.